time. We often imagine it as an arrow. It flies relentlessly in one direction, from the past, through the present, and into the future. This linear progression feels fundamental, an undeniable truth about the cosmos. But deep within the bizarre and fascinating realm of quantum mechanics, things get strange. Scientists have encountered phenomena that tug at this familiar tapestry of time. These quantum puzzles suggest something profound. The relationship between past, present, and future might be far more intricate. The quantum world doesn't always play by the rules we've come to expect. One of the most mind-bending ideas to emerge from these quantum investigations is retrocausality. Retrocausality proposes that events in the future can influence events in the past. Think about that for a moment. An effect could, in some subtle way, precede its cause. This isn't about changing history in the way movies depict. Instead, it's about a subtle, quantum-level influence that ripples backward through time. This notion is understandably highly controversial. It challenges the very foundation of our understanding of cause and effect. Yet certain experiments in quantum physics seem to hint that the universe might indeed have this peculiar feature. It compels us to reconsider the true nature of time and its role in the grand cosmic play. At the heart of quantum mechanics lies a concept called superposition. Superposition means that a quantum particle, like an electron or a photon, doesn't have definite properties until it's measured. Before we look, a particle can exist in multiple states simultaneously. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. A quantum particle is like that, but even weirder. It can be in multiple locations at once or spinning both clockwise and counterclockwise. Then comes the act of measurement. When we try to observe a particle in superposition, something dramatic happens. The superposition collapses. The particle is forced to choose a single, definite state. If we measure its position, we find it in one specific place. If we measure its spin, we find it spinning one specific way. It's as if our act of looking forces reality to make up its mind. This is where the first hints of retrocausality begin to surface. The choice of what we measure seems to play a crucial role. The strange part is that the particle had to travel through the experimental apparatus. We made our final choice of what to measure. It's as if our future decision influences the particle's past behavior during its journey. The renowned physicist John Archibald Wheeler was famous for his thought-provoking questions. He pushed the boundaries of physics with his Gedanken experiments, thought experiments. One of his most famous is the delayed choice experiment. It beautifully illustrates the quantum mystery we've been discussing. Wheeler took the classic double-slit experiment and added a dramatic temporal twist. He imagined a scenario where the decision to observe the particle's path or its wave-like interference pattern is made. The particle has already passed the crucial point in the apparatus. Imagine a single photon sent towards a screen. Before it gets there, it encounters a beam splitter. This device can either let the photon pass straight through or reflect it. If there's only one path to the screen after this, the photon acts like a particle and takes that one path. But if there are two paths and they later reconverge, the photon can act like a wave, seemingly taking both paths at once and creating an interference pattern. Wheeler's setup allows us to choose whether to recombine the paths or not. The choice made in the present seems to dictate how the photon behaved in the past. It's as if our present actions reach back in time to determine the nature of a past quantum event. The quantum eraser experiment takes Wheeler's delayed choice concept even further. It's arguably one of the most compelling and perplexing demonstrations of potential retrocausal effects. These experiments often involve pairs of entangled particles. Entanglement is another quantum marvel where two particles become linked. Their fates are intertwined no matter how far apart they are. The quantum eraser uses this entanglement to add another layer to the mystery of observing the past. In a typical quantum eraser setup, a photon passes through a double-slit apparatus. Normally, this would create an interference pattern showing its wave nature. However, the experiment is designed so that we can gain which path information. If we gain this information, the interference pattern vanishes. The photon behaves like a particle. The eraser part comes next, and it's where things get truly mind-boggling. One photon from an entangled pair goes through the slits. Its entangled twin, the idler photon, travels to a separate detector. Section 5. Echoes from Tomorrow, How Future Choices Ripple Backwards. The implications of experiments like Wheeler's delayed choice and the quantum eraser are profound. They strongly suggest that our actions in the present, specifically our choice of what to measure, can have a tangible influence on how quantum systems behaved in the past. It's not that the past is being changed in a gross macroscopic sense like altering historical events. Rather, the very nature of a particle's past state, whether it acted as a wave or a particle, whether it took one path or many, seems to be contingent on future measurements. The past, at this quantum level, remains unsettled until observed. It's crucial to understand that this doesn't mean we can send messages to the past. You can't use these quantum effects to warn your past self about a stock market crash or a bad decision. The correlations revealed by these experiments only become apparent after all the data, including the future measurement choices, are brought together and analyzed. Section 6. The Grandfather Paradox, Reimagined Quantum Consistency. Whenever we talk about the future influencing the past, the specter of time travel paradoxes inevitably arises. The most famous of these is the Grandfather Paradox. Imagine you build a time machine. You travel back in time. You prevent your grandparents from ever meeting. If they never meet, one of your parents is never born. And if your parent is never born, you are never born. But if you are never born, you couldn't have gone back in time to prevent your grandparents from meeting in the first place. This creates a logical contradiction, a loop that seems impossible to resolve. However, the kind of retrocausality suggested by quantum mechanics is very different from the macroscopic time travel of science fiction. Quantum retrocausality operates at the level of individual particles and their probabilistic behaviors. It doesn't imply that a conscious observer can travel back and alter large-scale historical events. The influence from the future is more subtle. Section 7. Novikov's Self-Consistency, a universe that prevents contradictions. Physicist Igor Dmitrievich Novikov proposed a principle that directly addresses the issue of paradoxes in scenarios involving time loops or influences from the future. It's called the Novikov self-consistency principle. In essence, this principle states that if an event exists that would cause a paradox or any change to the past whatsoever, then the probability of that event occurring is zero. It suggests that the universe is fundamentally structured to prevent such contradictions from ever arising. Physics, according to this principle, will conspire to ensure consistency. Applying this to hypothetical macroscopic time travel, if you tried to go back in time to kill your grandfather, the universe would somehow prevent you. Perhaps your time machine would malfunction, perhaps you'd slip on a banana peel at the crucial moment, or perhaps, more subtly, the conditions of the universe are such that only self-consistent histories are allowed. You can go back in time, but you can only do things that are already part of history, things that ultimately lead to you going back in time in the first place. You become part of a consistent, unbreakable loop. While Novikov's principle was initially discussed in the context of general relativity and wormholes, hypothetical tunnels through space-time, its core idea can be relevant to quantum retrocausality. Section 8. Beyond Theory, Technological Whispers and Philosophical Rumbles. While the primary implications of retrocausality are deeply theoretical, scientists and thinkers naturally wonder about practical applications, however speculative. Could understanding these temporal quirks lead to new technologies? It's important to be cautious here. We are far from building time machines or sending messages to yesterday. The retrocausal effects observed are subtle, statistical, and deeply rooted in the quantum realm. They don't easily translate into macroscopic control over the past, but that doesn't mean there are no potential avenues for exploration. Some have speculated that a deeper understanding of these temporal dynamics could, perhaps one day, contribute to advancements in quantum computing. Quantum computers already harness strange quantum properties like superposition and entanglement to perform calculations far beyond the reach of classical computers. If future states can influence past computations in some controlled way, even subtly, it might open up new algorithmic possibilities or error correction techniques. Section 9. The unfolding mystery: is time what we think it is? We've journeyed through some of the strangest territories of modern physics. We've encountered particles that exist in multiple states at once. We've seen how observing them seems to define their past. Experiments like Wheeler's delayed choice and the quantum eraser suggest something truly astonishing. Choices made in the present or even the future can apparently influence events that have already happened. This concept of retrocausality, where the future leaves its fingerprints on the past, is a profound challenge to our common-sense understanding of how the universe works. It's a whisper from the quantum world that time's story might be far richer and more complex than a simple linear narrative. Our classical intuition, honed by everyday experience, tells us that time is like a river, flowing inexorably from yesterday to tomorrow. But quantum mechanics, the most successful theory of the physical world we have, hints that this picture might be incomplete. At the fundamental level, the distinction between past, present, and future might not be as sharp or as absolute as we perceive it to be. The arrow of time, so central to our experience, could be an emergent phenomenon, a statistical effect that arises in large systems but doesn't hold true for the universe's most basic